In the next video, we would like to learn why containers are not optional if you are considering microservice migration. So moving on, so this is on the left side. If you have different WAR files from a microservice migration project, these are your options. You can deploy them to a Java enterprise application server like JBoss that will run on a virtual machine. That's your option. The problem is when you are separating 50 microservices from a single monolithic service, how many virtual machines can you create? Can you afford to create? So that is why containers are not optional. I have seen companies that have tried to run microservices on an IaaS, cloud IaaS system on individual virtual machines, and the cost skyrocket quickly. So that's why microservice containerization is not an optional thing. So on the right side, we can see that introducing Docker, it is pretty easy. So you will be able to reduce the number of virtual machines you will need, because containers are lightweight, and they will be able to run on the same virtual machines, or a much less number of virtual machines than you would have needed if you are trying to run them separately on individual virtual machines. So that's the reason, that's the motivation behind why containers are not optional or even affordable. Moving on, so let's try to understand the IaaS microservice deployment model a little bit. So you can see that I am deploying 3 instances of the application 1, and in 3 of them the architecture is pretty much same. It is the guest OS is installed on a hypervisor, and then the host operating system, infrastructure, network. The disadvantage is a big fat operating system is duplicated space and more money in OS license fees. That is why, and the thing that is not in this diagram, full feature virtual machine takes like 5 minutes, 4 to 5 minutes to come up, and that is why it's not a good choice for dynamic auto scaling up and down, because if you are hitting 70% traffic, 70% CPU or memory, and your cloud provider decides to auto scale, and if that auto scaling readiness takes 4 or 5 minutes, then the cause may be lost. That is why it may not be a good idea. In this architecture diagram, though, the operating system duplication is gone. So we are running on the same virtual machines. We are interacting with the host operating system with a Docker engine, which is lightweight, and our Docker container starts up within seconds rather than minutes. And this is not a new concept. The same shipping containers are transported, unopened through ships, trains, trucks, and airplanes. Why? Because the shipping containers are much more convenient to ship from one mode of transportation to another unopened. Same, the transportation company do not need to bother what is inside the shipping container. Similarly, your DevOps people, your developers, the moment they package their application in a Docker container, the DevOps people can deploy them to lower environments like dev, QA, stage, stress, or even production, without bothering about what is inside the container, what is in the application. The operations run up books, mode of operation becomes really, really simple. So that's another advantage. So moving on, so container orchestration and DevOps. So why we understood why we need containers, but why do we need container orchestration? So here is a little description. What the container orchestration tools bring to the table is something to be aware of when it comes to microservice operations. In real world, we have players who play different instruments, and then we have someone else who orchestrate multiple instrument players to produce melodious music. One little advice that I can give you, that whenever you are trying to understand the meaning of a terminology within information technology, make sure that you understand what that terminology means in your basic current understanding without IT in real life. I have come across the word orchestration multiple times since my childhood. I have known the names of orchestra players, and I have seen them operating large, directing large group of instrument players, and that's exactly what container orchestration systems like Kubernetes does in information technology. So if you understand why do you need a orchestra, conductor for producing melodious music, then you will readily understand why do we need a container orchestration master as well. So coming from the left, how do we run monolithic services? If the services run on-premise, the number of servers are often manually provisioned on a tool, using a tool like Chef, Puppet, or you can use Ansible maybe. IaaS not a good fit. Why? In the cloud environment, as APIs may grow in number, IaaS, which deals with direct virtual machines, may not be a good fit. How many VMs shall we manage for microservice deployment is an undetermined question often. Plus, running microservices on direct VMs is often an overkill. As I already said, they start very slow, they don't respond to auto-scaling really well. Docker comes to the rescue. When we understand that why IaaS is not a good fit for microservices, we Dockerize our services. However, only Dockerizing services may not be enough. Why? Container orchestration deals with managing containers automatically, making sure the desired number of containers for a certain service are always run. While this sounds simple, in practice it is an extremely complicated task. You wouldn't want to make sure these things manually. That's a huge headache. Other tasks, container orchestration tools like Kubernetes also perform load balancing, service discovery, security, property management, auto scaling, automatic blue-green deployment, routing, and many other tasks. Considering this, if you are a music player, you cannot play the guitar, the piano, the violin at the same time. You need somebody else. And that is why do not ever think about containerization without also thinking about an orchestration tool. Background, Kubernetes. Google has used the system behind Kubernetes named Borg to power their data centers for over 10 years, making this a highly tested system. Moving on. So there are a number of options for container orchestration, managed services. All the cloud providers support a managed Kubernetes service, including AWS, Azure, and Google. AWS also has Elastic Container Service, which came like 2015, which is similar. Azure provisioning tools. Some cloud providers like Azure provide ACS and AKS as tools to provision our own custom Kubernetes cluster if you don't want to go the managed service way. If the managed service do not meet our security needs, maybe. Kubernetes operations. That's a wonderful tool. COPS is a highly popular tool to provision a production-grade Kubernetes cluster on AWS with minimum effort. Last time I checked it supported only AWS. Maybe they have migrated to other cloud providers as well. Please check. KubeADM is Kubernetes' own tool that comes with manual provisioning. If we are interested in low-level provisioning configuration, I would say KubeADM is the tool that is used by SES, AKS, and COPS. Those are the high-level tools. Auto-scaled VMs for Kubernetes. You have the choice of enabling auto-scaling. The COPS tool add auto-scaling groups for adding VM capacity to the K8 cluster, or we can choose to add the VMs manually as well. Lastly, network access. Whether we manage the cluster ourselves or use a managed service, we may need to make sure that the pods running within the VMs in the cluster has network access to the other services, like your pods. I will explain what pods are. Your pods running on Kubernetes need to access databases running outside Kubernetes, so that's why you need to make sure the network access is really smooth. Moving on. So this is the Kubernetes architecture. So basically, if you consider the Kubernetes system, there are three types of nodes. One is the master node on the left side, and the other nodes are I'm sorry, not three types, two types of nodes. Master node on the left side and the worker node. So inside the master node, we have the API server. So what does the API server do? The API server actually listens to all requests from external clients, like kubectl is the tool that users use to connect to the Kubernetes cluster. So API server is listening to external requests for kubectl and internal requests from various worker nodes. Other than that, we have scheduler that schedules pods on different different worker nodes. The third component that we have running inside the master node is the controller manager, various controller manager for replication, namespace, service accounts. So the replication controller manager makes sure that if you want 5 instances of a 5 pods of a container running, then the replication manager will make sure that is what is happening. The namespace, say I have a pod, I have a microservice called product detail page, and you have a microservice called product detail page, but we are running on the same cluster. To resolve conflicts between your pod and my pod, Kubernetes introduces something called a namespace. It is very much like a Java package, and service accounts are authentication related. So on the middle, we have the etcd database, and that's where Kubernetes stores its configuration, and that's a cluster database. It's an open source, really highly reliable database. On the worker node, we have kubelet and kubeproxy. The kubelet component actually listens to the API server and the scheduler to communicate with the master node. And kubeproxy, that kubeproxy is a load balancer, is a stable load balancer, service accessor for pods. So what are pods? So when we deploy containers to Kubernetes, so Kubernetes surrounds them with another construct called a pod, right? So you may be running a single container within a Kubernetes pod, or you may be running multiple containers. Say you want to run a service that needs a MySQL database. So, and you want to run a MySQL container and your application container together. So what Kubernetes will do, they will run both container in the same pod. What is the advantage? Containers running in the same pod can access each other using the local host host name. That's the advantage. And there is a network, they will always be deployed on the same virtual machine, and the network latency is really low. So as I have shown, that there are multiple containers running on those pods. So kubelet is the, let me repeat, kubelet is the worker node component that is interacting with the scheduler to run those pods and reporting to Kubernetes master. The kubeproxy, now the problem of the pods is the pods definitely has a network address, but because pods are ephemeral, when they die, the network address is no longer reliable. So that is why the kubeproxy is a stable load balancer, service accessor to the outside world. So if you have pod network address, you want to access the pod using the pod network address, several minutes later you may not be able to access because the pods no longer survived. So that is why the external world needs a stable load balancer, stable proxy, which is the kubeproxy, and that is the little bit of high level of description for the Kubernetes architecture. Lastly, as I said, kubectl is a command line tool that people normally use to access Kubernetes cluster from command line. Of course, there is a Kubernetes console that you can access, which is a graphical user interface that interacts with the API server. So we talked about Kubernetes architecture. Let's see, where do we go from here? So I have described here in this table, the master node is a primary entry point from the outside world to Kubernetes. All external interactions happen through this node. API server is the REST API endpoints. These days, every software architecture has a REST API, and Kubernetes is not exception. etcd, the database. Kubernetes stores its configuration, how many pods, etc., how many when to run what. Scheduler schedules deployment of pods into worker nodes, has metadata about nodes. Controller manager runs multiple types of controllers such as replication controller, worker node. As I told you, the nodes that where pods run, Docker runs on each worker node. Kubelet gets the config for a pod from the API server and make sure the pods are running. Kube proxy, as I said, acts as a network proxy, load balancer, providing a stable network address. kubectl client-side tool admins used to connect to and operate Kubernetes. So let's see, where do we go from here? The video is getting a little longer. What I would like to do, I would stop here and start again in the next section, which is this microservice ecosystem. So thanks for listening. Let me know if you have any question. Post your comments, and then I will try to help you as soon as possible. Thank you. Bye.